The only voice in your last videos is yours and Nikki's.
Yeah, well, actually, last couple of videos have not been on, or ones we recorded. There have been old ones. This is going to be a new one because it's got some new stuff in it. All right, concentration of reactants is where we left. We left off with the three other ways. We have 4 ways we're going to affect the rate of reaction. And you need to know those, but there's not much to do with those. It took us 2 days to cover 3 of them. This is going to cover the rest of the chapter. Okay? The rest of the chapter we're going to be spending using concentrations in some way, shape, or form, a change in the concentration or the concentration itself, to actually do stuff with the reaction rates, the mechanisms, the orders, all the stuff that you don't, rate law expression, you don't know what they all mean yet, but that's what's going to be involved in the rest of it. There's some really weird stuff today that I wanted to go over with you because of stuff that a lot of people get wrong, and these are a lot of conceptual questions you'll get on kinetics. I was looking over the AP questions, and unlike thermo, where most of the AP questions for thermo, most of the AP questions involve some calculation of some type, right? A lot of these are conceptual. You have to actually ask you questions about it. All right, so let me show you, for example, with concentration. A lot of conceptual questions. When I ask them, you're going to get them wrong. You're going to get a lot of these wrong because the intuitive answer sometimes is wrong. All right. Well, first off, we should talk about what happens when you increase the concentration of the reactants. Obviously, that's going to make the reaction go faster. We can explain why, with the collision theory alone, it's going to be able to tell us that. The collision theory says in order for things to react, they got to first collide effectively. And, of course, if I have a higher concentration, I have a greater chance for an effective collision, greater chance for any collision. Okay? No one would get that wrong. Everybody would understand that if I increase the concentration of the reactants, I'm going to get a reaction that's going to happen faster. That's not the problem. The problem is there's a necessary corollary to that you don't realize when you write that down or when you're thinking about that. And the only way I can illustrate, the best way I can illustrate that is with an example. That's what I'm going to do. Okay? I'm going to illustrate this with an example. Let's just use A, B, and C as my A plus B yields C. Go where? All right, A plus B yields C. All right. Now let's say that you don't need to make these boxes. Okay, you just need to. There are going to be boxes that are going to come up this way. It's the only way I can get them to do this. All right. You just need to fill in the numbers below. You don't have to put a box around. Let's say I start off with the initial amount of A. I have 1 molar of A and 1 molar of B, and I mix these two guys together. They're in solution. And I have 1 molar of A and 1 molar of B. 1 mole per liter of A, 1 mole per liter of B. I pour these two guys together, equal amounts, and at time 0, the initial amount, before they actually react, how much C will I have? No. Now, I get all kinds of bad answers for this. That's one of them. She said 2. So did you. Say 2. That's a very bad answer. Stoichiometry does not say 1 plus 1 yields 2. So then I got another bad answer. Well, 1 to 1 to 1, so the answer would be 1. Not initially. I'm saying before they actually hit. I pour them together.
0.
0. Exactly. The answer is 0. I don't have any product yet. Okay? I have, I always use, these are mostly going to be gases. Okay? But it's easier sometimes for you guys to visualize pouring 2 liquids together before they actually hit. Before they actually touch. I don't have any C. Okay, so that's your first mistake. I saw both answers, both wrong answers. 2 and, 1, which we in stoichiometry, wrong answer. Now let's say we wait a certain amount of time. We'll call it time X. A certain amount of time goes by. Maybe a second, maybe 20 seconds, maybe 5 minutes. Whatever it is. Okay? I wait some amount of time, and after that certain amount of time, I now have 0.5 moles of A and 0.5 moles of B. Let me ask you. How much C did I make in that time? What do you think? 1 is the classic answer, and it's wrong. Again, let me show you why. It's the easiest way to show you is with the little marbles here, these little balls. 1 carbon, it just makes sense. 1 carbon plus 1 oxygen would give me 2. But 1 plus 1 is 2. But 1 carbon and 1 oxygen gives me how many carbon monoxides? 1. 1 carbon plus 1 oxygen gives you 1 carbon monoxide. It's not additive. So 0.5 moles of A were used up, 0.5 moles of B were used up. How much C, when I put them together, did I get? 0.5. Okay, so there's your second mistake. I told you this is just chock full of dumb mistakes, and believe me, the AP questions will try to get you to make these. I've been reading them. They're going to try to get you to make these dumb mistakes. And they are dumb if you think about it. I mean, to say that there's initial amount of the product is 1 or 2, it's got multiple mistakes in that. The initial amount is 0. All right. Believe it or not, all that I just did here has nothing to do with what I'm talking about with kinetics. It has to do with the third thing I'm about to say right here. If I wait for time 2x, so half of it was gone in time x, here's the next classic example. How much will be left if I wait for another x? 0, right? It's all gone. Here comes the second part of this statement. If we all agree increasing the concentration of the reactants increases the rate, then what must happen if the concentration of the reactants decrease? The rate decreases. Is the rate going to be the same from here to here as it was from here to here? No. It's going to be half the rate it was. So I'm going to end up with 0.25 moles of that, 0.25 moles of that. You see where I'm going to. Where I'm getting at.
It's the inverse square law.
Well, kind of. It's a math equation where we're going to be approaching 0, right? But never really reach it. That's in math class. Unfortunately, we live in the real world. In the real world, you say, well, I can keep doing this forever, and I'll never be able to end it. I'll never get to 0. And in math class, you're right. But in reality, in chemistry, you do eventually get to 0. If the reaction goes to completion, you do get to 0 for this reason. I can divide a number in half infinitely, right? Doesn't matter how many times I divide it in half. I can always divide a number in half. But if I'm talking about how many molecules I have, all right, and I start off with 10 of these and 10 of these, and I use up half the first time, then I use up half over the next time, and then eventually, what's going to happen? I'm going to run out of molecules. There's going to be no molecules left. So in reality, math isn't like science. Science deals with real numbers. Math deals with numbers that only can exist in the negatives. Can we ever have a negative concentration? You can never have a negative concentration. And we also can't have a half of an atom. So for those reasons, because there is a limit to chemistry versus math, that we eventually would get to 0. However, I bet you're probably figuring out what this is going to graph like. I'm going to graph this in a minute. Before I do, here's the corollary to that statement. If the rate increases with increasing concentration of reactants, guess what? The rate of the reaction must decrease as the reactants are used up. And therefore, it's changing all the time. It's always changing. Does anybody realize, anybody thinking ahead about, geez, what kind of math would I have to use to solve these kind of problems? Where I have multiple things changing continuously. What kind of math would that be? Would it be algebra? No, what would it be? Calculus. Yeah, who's in calculus in here? Okay. Now, don't worry, we're not going to actually do calculus problems with it, but I am going to kind of hint at them and show you some graphs and some other things. But we're not actually going to do derivatives and stuff like that. But you can solve these problems by that. So the rate of the reaction decreases as the reactants are used up. Therefore, you're not going to get a linear change. The reaction rate does not change in a linear fashion. You're going to get a graph that approaches 0, and it's going to have a different shape than just a straight line, as you'll see. But I don't want to give that shape away. I want you to see it. Today's all about you guys making those common, obvious mistakes and then correcting them so you don't make them again. You've already made several of them. Stoichiometry doesn't say 1 plus 1 equals 2. Stoichiometry looks at the coefficients. Okay? Your initial amount cannot be what the stoichiometry is because you didn't start it yet. And finally, the rates don't change the way you think. They're constantly changing. If I use this up, I'll have a slower rate now, so it's going to be even less, and then less, and then less. Okay. All right. Let's do this. Let's graph this. Write this down. The rate can be measured by observing how fast the reactants are used up or how fast the products are formed. If I graph it, I get another very common term from geometry class. I'll bet you realize it in a minute when I put it down here, when I graph this. I'm going to show you how we can get the actual rate from a graph. And by the way, the reason I'm showing this is because it's exactly what you're going to be doing in the lab. We're going to be producing oxygen gas at a rate. We'll be taking the measurements. We'll be graphing it, and we'll be seeing. We'll be able to determine the rate of that reaction from the graph. What about the graph? Well, let me show you. Let's do an example. Let's use a real-life example this time. Some real chemical. I'm going to use the same exact equation for the next 3 examples I do. First, I'm going to graph it, and then I'm going to ask you several questions about it. And this is a good one, although I left out the G's. These are all gases, and it's a good one for that reason. I see this in a lot of books. You see this in a lot of example questions. It's a classic example. You'll see this probably. Good chance you'll see this one on an AP question. Okay, so I take N2O5 and I break him down, decompose it into NO2 and O2, and there's the balanced equation. I'm going to graph it. I have 3 different colors, but you guys are going to use 3 different symbols. We'll use a circle for this guy. Okay, I'll use a triangle for this guy, and I'll use a square for that guy. So you put that as your legend underneath each of these. He's your circle, he's your triangle, he's your square. And then I'm going to graph it for you. Copy this. Before you copy, let me show you something. Pretend that's your paper, and these are the lines in your paper. Okay? Okay, that's how big I want you to make it, and I want you to label everything, including the numbers on here, and the time 0, time 1, time 2, so on. Okay, after you copy that, you don't need to draw the lines in. Your paper will act as those lines. Keep you on track. Let me ask you some questions where we're going to get, again, those answers. Well, gee, oh yeah, I should have known that. Let me assume we start with what I'll call stoichiometric amounts. In other words, these coefficients will tell me how many moles, all right, we're going to be using and getting from our answer. So let me ask you. Where will I put my first circle for N2O5 in the beginning before it starts to decompose? Where will I put that first circle for N2O5 on this graph? Well, it's going to be at time 0. Where on here? Everybody says 2. Same exact. Before it actually reacts. Oh, yeah, you're right. I'm sorry. 2 is correct. I was almost ready to. I was waiting for you guys to spell. Good. 2. It starts at 2. Let me use red, and there you go. I'll put my circle there. Where does NO2 and O2 start? That's what I was kind of getting ahead of myself, waiting for you to make it. I was anticipating your mistake before you made it. Yeah, he starts at 0, not at 4 and not at 1. He starts at 0 before I've actually produced it. You see what I'm saying? So there's my box, there's my triangle at 0. Here's my circle, N2O5, at 2. So I put 2 moles of N2O5 into a box, into a container. And I wait. I do something. I add a catalyst, whatever. And I let him decompose. And when I'm all done, I'm going to end up with NO2 and O2. So when I'm all done, where will my red circle be? So assuming time 4 is the end of the process, I'll have a red circle down here. Okay? And assuming time 4 is the end, where will my triangle, my blue triangle be? Everybody agree it'll be up here? At 4. And my black square will be, I hope you all realize right there. Got it? All right. So now comes the $1 million question. How did they get there? What does the graph look like? And let's start with the red one. There are 3 possibilities for this guy. Okay? He could go like this. Right? Straight line. That's supposed to be a straight line. So it could be a straight line. Okay? Do you think that's right? No, it's definitely not right. So I need you to think about what the graph might look like. It might be this, because we know it's going to be curved, or it might be that. You know it's going to be curved. Which one do you think? The red, the black, or the blue is the correct answer? The blue one. Absolutely. Very good. Let me erase those now. Very good. Okay? So, he starts at 2, and let me explain why you would know that. In the beginning, between, let's just say half of it gets used up. The rate's really fast in the beginning. So between time 1, let's say that's the actual half one. So between time 0 and time 1, I use up half of it. Okay, so it drops that much. But then, what happens? Only half again for the next one, and then half, and so on. And that's why in the beginning it's, and by the way, I'd have to have a lot more to work it out correctly, but that you get the idea of what the shape should look like. What do you think the blue one should look like? Would that be like this, straight, or like that? Think about it. If it's reacting quickly early on, yeah, it's going to be this way. Fast at the beginning and then tails off at the end. See it? And finally, where would the black one go? Look like same exact way, because he's a product. Fast in the beginning and then tail off at the end. Isn't that cool? I actually have these guys done for me on the graph, but they're choppy. That's why I wanted to make sure you didn't draw it choppy like that. All right, I wanted you to see it. But I also wanted to have that so I could show you some stuff on it. Let me show you. Okay. Does anybody see now how I can get, if I graph concentration of the reactants versus time, what I could do to get the actual rate of the reaction? Because remember, the rate of the reaction is how many moles per liter per time, per second, I'm going to actually get. So what would we call that if we were back in 9th grade geometry class? We call it the slope. Now, the bad part about this is, guys, in 9th grade geometry class, you only dealt with those kind of slopes. Nice linear slopes. Changing y over changing x, right? Well, look at what the slope is in the beginning. In the beginning, the slope's really fast, right? Really steep. Less. It changes as it goes on. That's the calculus part of it. Isn't that fun? Yeah. And let's notice something else about the slope. Which of these would be correct, the correct sign for the slope? The blue, the red, or the black? No. Because what kind of a slope is that? Negative. You see? I cannot have a negative rate. I have to have a positive rate. So only the blue and the black have the correct sign for the slope. And remember, the slope is just change in y over change in x. Where y, in this case, is the concentration, and x is the time. How about that? So you're actually using geometry, although really you're using calculus. Calculus, math, all to solve these problems and using it, thinking about it in your head. So, all right, good enough. Now, what kind of questions can I ask you regarding? Well, I've already asked you some like this. I'm going to give you an example in a minute. But let's write all this down, because I've been telling you a lot of information, but I haven't written much down. I just wrote the graph. Okay, so let's write all this down. The rate of the reaction is the slope of the tangent. By the way, you know what a tangent is, right? It's the tangent to that curved line would be the place where it intersects, at a perpendicular angle at any point, right? So that would be the slope of that tangent line. So it's constantly changing. And it has to be the curve of the products. The curve of the reactants are going to be the negative of that slope. Because, as you saw, what happens when it looks like the curve of the reactants. So you could write the equation like this. The rate equals change in y over change in x, which is basically the slope. And in calculus, what's that called? Delta y over delta x. What's that? Point slope? Well, yeah, it's true. At a given point. Or, yeah. Matter of fact, I'm going to talk about something called the integrated rate equation. I'm not going to actually make you do it, but we are going to end up. I'm going to make it derive it. but we are going to end up using it to solve for half-life problems. Can you derive it? Colin can. You probably can. All right. So the rate equals the change in y over the change in x, which is the change in the concentration of the products over the change in time. Now we did, just the other day, I want you to think back. I want to put this into context. We were able to get a very simple rate doing that temperature lab, and all we did was we didn't care about the concentration of the product. We just cared about how much oxygen was produced. So we measured how many milliliters of oxygen per time. Rates are always going to be per time. Well, to do it right, you got to not have just the volume, but you have to actually have the concentration, moles per liter. You have to convert it to moles per liter, okay? Not just how many milliliters you have. By the way, just real quickly, if you use the reactants, you're going to have to use the negative value of that slope. And these, believe it or not, I was looking through, and that's why I've added. That's why I'm recording this one again. I didn't really give examples of this. I just assumed that you would understand it in the past. And before the AP exam, I didn't stress this very much. But now I realize there are a lot of questions, a lot of conceptual questions based on that graph, slopes, all right, and being able to determine the concentration changes per the rates given some actual data. So I'm going to do two examples for you. One is, how would you set up the actual equation? And the other one, if you're given numbers even, could you do it? Okay? But that's everybody understands where all this hopefully came from. All right? Now, let's do the two examples. Let's start with this one. Write that example down. This is the same kind of question you're going to get in the homework tonight, 7 to 10. There aren't many questions, and they're not very long. You will not actually have homework. You're going to probably... I'm not going to be here tomorrow, and I won't see you anyway. Christmas break, so eventually, you'll have to do these. Notice I use the same equation. Okay. If I were going to use these three guys to express the rate of the reaction, I want you to tell me, first of all, who would be the easiest one to use because of whether he's a reactant or product and because of his coefficient. What do you think? O2. O2 has a coefficient of 1. Yes, that does matter. Okay? And secondly, O2 is a product. So let's do O2 first. If I were to express the rate of the reaction, I could do it if I knew the concentration change of oxygen per time. And how would I write that? The rate would equal the change in O2 over the change in time. Kind of like I just said. That was the most obvious answer. But the reason I'm doing this, I noticed on the AP questions and all that other stuff I've been looking at, they aren't going to ask you the obvious one. They're not going to give you the easy one. They're going to give you one of these guys. And they're going to make you think about it. Here's what I want you to do right now. Okay? I want you to actually open to page, there's a little analogy there. On page 600 and, God bless you, 610. And don't get hung up on the pickles.
Where?
Yes, there are pickles and sardines in there. But I want you to read that. Read that little analogy in that box. Just a little thing in the green box. Very short. And all this is explained. It will be done in 1 minute. No, survive. 1 minute. Read. Open to page 610. 610. You reading that? That'll be for you. Hello. Alex. Yes. Yep. Okay, bye. They can wait. The longer you do this, the longer you're going to be. Just wait. All right. So basically, 2 slices of bread, 1 sandwich. You know, you're using up that bread twice as fast. So if I were going to use, I forget which one I do next. I don't know if I do this one next. I think I do this one next because he's still positive, correct? He's still positive? Yeah, so I'm doing the NO2 next. What would you actually have for the rate in this case? What's it going to be? Not. Read it again. Look at the bottom. It's going to be 1/4, whatever the concentration change of NO2 is. You see, again, you're making all those common mistakes. And you know what they're going to have as those answers? They're going to have an answer that's 4 times and 1/4. And you got to know the difference. Okay? You got to know the difference. Lastly, what's the big difference between using that guy? Not just that it's going to be 1/2, but it's going to be negative. Negative 1/2 times the concentration change of that guy. Because I'm using 2 slices of bread per sandwich. Okay, as it shows you in that little analogy. Have a Merry Christmas, Olivia. Okay? All right. Now, there's another way I can ask the question, though. You watching? That's to get the rate. All right? But there's another way I can ask this question where I actually give you numbers. And you have to use stoichiometry to do this. Watch. I mean, stoichiometry is easy. We know how to do stoichiometry. We've been doing that forever. Copy that guy now.
You only have a single day?
Yeah, we're almost done. This is the last example, then I'm done.
Because I have to deliver pizza to people.
You giving the rest of that away?
No, I'm just giving those 2 pieces right there to people.
What 2 pieces?
I wondered why they.
Well, there's like 5 more left. Take them.
I don't eat them.
Anybody else who needs them can take them. I'm taking the sausage home, though.
Okay.
That's my favorite.
I'll take it, I guess. Because Mrs. Phillips wants some, and the people in Mrs. Phillips said that they could take me.
Well, when we're done here, anybody wants some more pieces to take?
Yeah. I just need those 2 pieces, to be honest.
Okay. All right. So this time I'm saying find the rate of the reaction for each compound if I'm told the NO2 is being produced at that rate. Okay? How would you know how to use that? Use the other guys to tell the rate. Well, this is just a stoichiometry problem. That's all it is. It's very simple. Well, guys, we're doing stoichiometry. All right, we've done stoichiometry all of last year, and we even used it for fermentation lab.
From Chem 1.
Fermentation lab, we just use it for. Remember? To get how much alcohol, theoretically, we should have got. All right, let me ask you this. What's the main goal of stoichiometry? Go from what to what?
Moles to moles.
Moles to moles. Okay? Regardless of anything, what you're given, you can be given grams, you got to convert it to moles first. You're given liters, you got to convert it to moles first. You're given molecules, you got to convert it to moles first. All right? And then, once you're in moles, you can convert using, what do you use when you go from moles to moles?
The coefficient.
Yeah, the coefficients to be able to convert from one to the other. So, for example, if I told you you had 8 moles of N2O5, don't do this. If you had 8 moles of N2O5, simple question. How much NO2 would be produced? 16. 2 is to 4 as 8 is to 16. Or, you don't want to do it that way? Fine. 8.0 moles of N2O5 times, what goes in the bottom?
N2O5.
Moles of N2O5.
Yeah.
And I'm looking for this guy, so moles of that guy on the top. How hard is this? 4 over 2, 8. Right? Pretty simple. So in this case, what am I told? I'm told I have 0.0072 molar of N2O5 per second. and I simply put molar of N2O5 on the bottom, and molar of, who am I looking for? NO2 on the top. What put?
Would it be NO2 and then NO5 on N2O5 on top?
Yeah. N2O5 is on the bottom because it has to cancel. NO2 is on the top. That's what I'm going. Oh, wait, what was I given? Oh, I was given NO2. My fault. Okay, so 0.0072 molar of NO2. That's my fault for writing it down per second. Sorry.
You just killed Trent.
Yeah, sorry, Trent.
He's not going to.
And Dante. So molar of NO2 on the bottom. That's your given. And by the way, why does molar of NO2 have to go on the bottom? What is it going to do? It's got to cancel. Molar of N2O5 on the top. And coefficients. All the coefficients.
Taking a half.
2 in there, 4 there, and you get your answer.
Well, what's the answer?
Whatever, you did a calculator. You got a calculator. What's 1/2 of 0.0072?
0.0036.
0.0036.
Then what's that the answer for?
Molar per second. That's your rate if you were to be using NO2.
Oh, not that?
Or N2O5. And what would I do to get oxygen, people? Yeah. I told you it wasn't hard. Molar of NO2 on the bottom, molar of oxygen on the top, 1, 4, and so what's half of 0.0036?
0.018.
0.0018.
Damn, that's actually not hard at all.
I know. Now, remember, that's the kind of questions you'd be asked, the multiple choice kind of sections. All right, those are the kind of questions you'd be given, kind of conceptual, kind of thinking about it. Okay, what do you think would happen if you were to, try to apply the the slope to this guy? Okay?
Cool.
All right, let me stop this. Homework's on the board, 652, numbers 7 to 10. Page 652, and that's for people who are at home, because I didn't write this down, I think, on their card. Page 652, numbers 7 to 10.